Students, this is Dr. Nikara, Geochemistry Mentor, welcoming you for another session in hydrogen bonding. Today we are going to see the importance, that is, consequences of hydrogen bonding. Okay. So under the importance of the significances of hydrogen bonding, the first point is dissociation. Okay. See, in dissociation, for example, when HF is dissolved in water, it dissociates into difluoride ion, that is HF2 minus instead of F minus. Okay. To HF, this on dissociation gives H plus HF2 minus. Okay. Actually, this is abnormal behavior. Okay. Normally, we used to get F minus, H plus F minus, but we are getting HF2 minus. So this is an abnormal behavior, and obviously, this is mainly due to the hydrogen bonding existing between hydrogen and a fluoride. Okay. See here, this is the type of bond we are having between hydrogen and fluoride. Since because we are having this hydrogen bonding between this hydrogen and fluoride, we are getting HF2 minus instead of F minus. So this is an abnormal behavior. Okay. Actually, this abnormal behavior of HF is responsible for the existence of KHF2. Okay. But similar compounds like KHCl2 or KHBr2. See, these type of products are not possible. That is, they do not exist due to the absence of hydrogen bonding in HCl and HBr. Okay, the reason why we are not having these two types of compounds is the absence of hydrogen bonding in HCl and HBr. The reason is this chlorine and bromine, they are having huge size when compared to fluorine. So the distance between the nuclei and the valence electron in Cl and Br is too high. So hydrogen bonding is not possible in the, so this type of abnormal behavior is observed only in hydrogen fluoride and not in HCl or HBr. Can you understand? The next important consequence is association. Say due to intermolecular hydrogen bonding, two or more molecules of a compound exist as associated molecule. Can you understand? Because of this intermolecular hydrogen bonding. Since we are having intermolecular hydrogen bonding, two or more molecules will combine and exist as associated molecules. Okay. For example, carboxylic acid. Okay. See here, these carboxylic acids, they exist as dimers. Okay. See here, this is one carboxylic acid or COOH. Okay. Or COOH. So these are the two carboxylic acids. They are existing as dimers. Okay. This is because of the presence of hydrogen bonding between two carboxylic acids. Okay. Since because these carboxylic acids are existing as dimers, their molecular masses are also getting doubled. Okay. For example, acetic acid, that is CH3COOH. Okay. This acetic acid molecular mass is actually 60. Since because it is existing as a dimer, its molecular mass is double, that is 120. Okay. So the association also affects the strength of the acid. Can you understand? Next important point is high melting and boiling points. Okay. So the compounds containing hydrogen bonds possess high melting and boiling points. Okay. For example, the compounds containing hydrogen bonds possess high melting and boiling points. Okay. See here, this is ethyl alcohol. Okay. This is that is a CH3, CH3, CH2OH. This is CH3, CH2OH. Okay. See, actually, this ethyl alcohol, it has a higher boiling point than compared to this diethyl ether. This is diethyl ether. Okay. The reason is in ethyl alcohol we have hydrogen bonding, whereas in diethyl ether we don't have. Okay. This diethyl ether doesn't have hydrogen bonding. Actually, this hydrogen bonding raises both melting and boiling point of a substance. This is because the hydrogen bonding are strong intermolecular attractive forces, and this creates a stable molecule. Okay. So it takes more energy to break up such molecule than it would if the bonds were not there. Can you understand? That's why this ethyl alcohol, it has high melting as well as boiling point when compared to diethyl ether. The same thing we could observe in water and H2S. Okay. See here in water molecule we have hydrogen bonding. This is water molecule, we have hydrogen bonding, whereas in H2S we don't have hydrogen bonding. The same thing we can explain in the case of ammonia and then water molecule and then HL. Okay. See, all these molecules, they have a high boiling point as well as melting point due to hydrogen bonding. Can you understand? Next, we shall see about solubility. Okay, say a substance is soluble in water only if it forms hydrogen bonding with water. Okay, say here this is alcohol. This is CH3, CH2, OH. Okay, that is ethyl alcohol. CH3, CH2, OH. Okay, see this ethyl alcohol is forming hydrogen bonding with water molecule. Okay, these alcohols are soluble in water. This is due to the reason is the hydroxyl group present in the alcohol is able to form a hydrogen bond with the water molecule. Okay, so both alcohols and acids, they have this OH group. So these OH groups, they have the capacity to form a hydrogen bond with water molecules. This is the reason why alcohols and acids are more soluble in water. Can you understand? When you are taking into account alkanes, alkenes and ethers, okay, see these are insoluble in water. They are not soluble in water because they don't form hydrogen bonding with water. So all these substances, they don't form a hydrogen bonding with water molecules. So this is the reason why alkanes, alkenes and ethers are not soluble in water, whereas these alcohols and acids are more soluble in water. Can you understand? Next important significance is high viscosity, heat of vaporization and low volatility. So the molecules which are capable of forming associated molecules through hydrogen bonding have naturally low volatility, high heat of vaporization and high viscosity. Okay, see this is quite obvious because this hydrogen bonding, it keeps the molecules so intact that we have to spend high energy or amount of heat energy to break the bond. So this is the reason why they are having high heat of vaporization and low volatility. Let me take an example for this glycerol. CH2, OH, CH, OH, CH2, OH. See here in glycerol, this is glycerol, okay. This is more viscous due to the presence of three OH groups. This can form a number of hydrogen bonds per molecule, okay. But when you are taking into account the next one, that is a glycol, see ethylene glycol, CH2OH, CH2OH. Okay. See here we are having only two OH groups. So automatically the number of hydrogen bonds will be lesser when compared to glycerol. So this is less viscous, whereas this glycerol is more viscous. The same thing we can explain for volatility. Okay. Since hydrogen bonding is more in the case of glycerol when compared to glycol, we need to spend some more energy so that only then it is possible to break the hydrogen bond and then it is possible for the glycerol molecule to get escape or vaporize. So low volatility. Okay. So low volatility, high heat of vaporization and high viscosity due to the presence of intermolecular hydrogen bonding. Can you understand? Next important point is strength of certain acids and bases. Strength of acids and bases can be explained on the basis of hydrogen bonding. Okay. When do we call a substance as an acid? An acid is any hydrogen containing substance that is capable of donating a proton to another substance. Okay, we call a substance as an acid when it has the capacity to donate a proton or a hydrogen ion to another substance. Okay, and a base is a molecule or an ion which are capable of accepting a hydrogen ion from an acid. Okay, so here let me explain the strength of the acid by taking an example, that is salicylic acid. Okay. See here we are having three isomers of salicylic acid. See this is ortho, this is meta and this is para. Actually the salicylic acid is a stronger acid than when compared to the meta and para isomers. This is because this salicylic acid easily furnishes H plus ions as a salicylic and it forms a salicylate ion, and the salicylate ion formed is stabilized by the intermolecular hydrogen bonding. Okay, see here a salicylic acid, it can easily furnish H plus ion. Okay, after furnishing this H plus ion from here, this forms a salicylate ion. Okay, this forms a salicylate ion. In salicylate ion, we could see the intramolecular hydrogen bonding. What is the intramolecular hydrogen bonding? The hydrogen bond formed within the molecule, not with the other molecule, within the molecule. Okay, So since because the intramolecular hydrogen bonding is there, this particular ion, that is salicylic ion, is more stabilized. Okay, but whereas this such stabilization is not possible in meta or para isomers. Okay, that's the reason that although salicylic acid is more stronger when compared to meta and para, because after giving up H plus ions, it should be in a stabilized form. The ion formed by the acid should be in a stable form. Whereas this in this case meta or para, it is not possible. Can you understand? Thus the strength of the acid is explained on the basis of intramolecular hydrogen bonding. Can you understand? Next we shall see the unique properties of ice. That is why the density of ice is lesser than water and why the density of water is maximum at 4 degrees centigrade. Okay, and actually the reason why the density of ice is lesser than water is it is having an open cage like structure. Okay, the ice is having open cage like structure due to hydrogen bonds. In ice, each water molecule is linked tetrahedrally to 4 water molecules. Thus, the molecules are not so closely packed as the case of liquid state. Okay, so the molecules in ice are not so closely packed as in the case of liquid state. See, when ice melts, the cage-like structure is lost. Okay, and the molecules they come closer, they come nearer to each other. Because of this, the volume of the same mass of water decreases. Okay, actually, density is nothing but it is the ratio between mass and volume. Okay, mass by volume. Density is mass by volume. Okay, so when ice melts, the mass will be remaining the same, whereas when the ice melts it becomes liquid, its volume decreases. When its volume decreases, automatically the density will be getting higher. Okay, density increases. Okay, next comes why the density of water is maximum at 4 degrees centigrade. See, on heating, the cage structures collapses and this continues up to 4 degrees centigrade. Okay, 4 degrees centigrade. At this temperature, the volume becomes minimum. At 4 degrees centigrade, the volume becomes minimum for the definite mass and density becomes maximum. So at 4 degrees centigrade, okay, at 4 degrees centigrade, the volume becomes minimum. So that's the reason why the density of water is maximum at 4 degrees centigrade. So, on heating the ice, the cage-like structure collapses. This continues up to 4 degrees centigrade. Okay. At this temperature, the volume becomes minimum for the definite mass and the density becomes maximum. Can you understand? Well, fine students, I hope you might have understood what I taught today. Let me meet you with another important topic, that is types of van der Waals forces, in my next session. Until then, it's Dr. Anitha, geochemistry mentor, signing off from you. Thanks for watching.